I gotta read the questions. You give out the coins. I know, right? It's about to be. All right, one more question from War Games. David discovers the password gaining access to the Whopper account. The computer asks David if he would like to play a game. What game does David prefer to play? I heard it first here. I know, it's an easy one. I'll get some more difficult ones. Ready? Okay, cool. Get in behind you. In the hat, right behind you. What's that? No, it's just a little. All right, so I'm going to introduce our next speaker. This is our last talk before lunch. The speaker's topic is, as you can see, our Docker app got hacked. Now what? Which I don't understand because Docker's super secure. I mean, it's completely secure. Right? Joel has his master's in crypto analysis. He also dabbles in reverse engineering and forensics analysis, malware counter-exploitation, malware obfuscation, evolution, and botnet neutralization. Welcome, Joel.
So as you can see from the slide, this is going to basically be talking about what you do after someone's Docker app has been hacked. Because as we all know, they're not always the most secure. They're better than some things, but not always the most. So right off the bat, that is a link to all the slides I'm about to go through. The reason I'm putting it up there first is because there's going to be a lot of terminal session screenshot type things, a lot of text. I've tried to make it as large and legible as possible, but I realize not everyone's necessarily going to be able to see it well. So if you want to even just download it right now on your phone, you can. So I'll leave that up there for a second. While it's up there, I'll give you a little bit of a story as to why I'm giving this talk. Basically, something along the lines of what the title happened. I run a small cybersecurity company that, among other things, does forensics. And one particular day, one of our partners reached out to us and said, hey, we've got someone who was running a bunch of Docker apps on a server, and it got compromised. And now they need to know what happened. You know this Docker stuff. Can you guys take care of it? Okay. So one fine summer day, I found myself staring at a host image that had a whole bunch of Docker containers on it. And I had to figure out, well, how am I going to go forensically pull out the information for what went on and figure out, basically what was the story here. And of course, the first thing you do is you sit down and say, okay, before I reinvent a bunch of wheels, let's go see if someone else has made some tools. So you Google it. And Google came back with nothing. By the time I was done, I'd spent a reasonable amount of time in the Docker source code sorting through how all this stuff worked. And when the B-Sides call for proposals came around, I thought, maybe I can save someone else the trouble of having to do this the hard way like I did. So, the goals for this talk basically are going to be, if you find yourself in a position where someone's Docker app got hacked and everyone's looking at you and saying, what happened? How can you go pull out the forensic information necessary to work out an answer to that question? We'll cover what it's like for a live system, which is the easy case. That's one slide. And then we're going to spend a lot of time on what to do when you've basically been handed a cold hard disk. Yeah, there were some Docker apps on this. Tell us what happened. Not quite as simple. Specifically, Docker has a lot of different storage backends, which is how they store the disk state for a container and images and whatnot. We're only going to cover two of them, but they're going to be the two that you're most likely going to run into. The OVERLAY2 backend, which is the default one that they're pushing everyone towards, and the DEVICEMAPPER backend, which is the one you're going to run into on certain versions of Red Hat Enterprise Linux or CentOS. There are others, but if you wind up in this position, you're probably going to be dealing with one of those two. So, to start off, just to review, what's a Docker app? A Docker app basically, or a running Docker container, is really nothing more than, at least on a Linux system, which is what we'll be looking at, nothing more than an ordinary Linux application that's running, with two caveats. One is there's that nice little box around it, which is basically the Docker daemon using a bunch of Linux kernel primitives to say, okay, we're going to try to make you think you're in your own world. As Dan Walsh famously said, containers don't contain, so that is a little bit leaky, but it's pretty good. And then the second part that makes a Docker container is that this application that's running gets its own dedicated view of what it thinks the file system is. And what's of special interest to us in this case is that the way Docker does that is by kind of stacking layers on top of each other. So instead of just saying, here is a flat directory with your file system, we're just going to like chroot into it and off you go. They maintain things in a bunch of layers, partially so that they can have a base image they can reuse many times, and then all the writes that individual containers do are specific to those containers, and partially due to some of the development-oriented priorities they had when they originally designed stuff. From our perspective, basically, for a live system, we're either going to be dealing with, all right, we got that entire picture, so what can we grab? For a cold system, we're just going to have those little boxes underneath the foo process, which is the different disk layers that make up the foo process's view of a file system. So live capture, how are we going to do that? Well, thankfully, Docker makes this fairly simple. We can actually do live capture almost entirely with just plain Docker commands. It turns out when you run a container, almost all of the relevant metadata for what's there can be dumped out with the docker inspect command. That's going to include what image, what file system layers that you start with, was the container started on, what did they run, what directories from the host file system or somewhere else did they mount into the container, what kind of privileges did they give it, what were the environment variables, the whole 9 yards. So that's one thing you'll definitely want to grab if you're dealing with a live system that you can control. The other nice thing is that Docker also logs all of the output, standard output and standard error from any container. And if it's got a terminal attached to it, you'll get the input too. So the Docker logs command will give you a nice dump of that. That can be especially useful in situations where someone has compromised a host and then promptly turned around and run more Docker containers of their own, or maybe that's how they got into the host. Oftentimes they'll run a perfectly benign container, like just a base image container, like the Ubuntu one, image. But they'll have a terminal attached to it, and then they'll pump in, a couple commands saying, like, go download Python. Here's this teeny little Python script that's going to basically just set up a port forwarding shell. Off we go. In that case, if you were to go look at what was on disk, you might not find a whole lot. But being able to look at the terminal I/O can be incredibly illuminating. Then in terms of how do we actually get what's on disk for a given container while it's running, this is where the design of Docker and their mindset for making it kind of like a development packaging system more than a secure containing system comes into handy. The way images are built is by running containers that do individual commands, and then each time a container is done, you take that little ephemeral read-write layer and you commit it, and it's just a new layer built into the image. And so when you're done, you've got this image composed of a whole bunch of little layers, each representing the changes from running a specific command. Because that's how images are created, it makes it very easy for us then to capture the disk state of a running container. We just commit it. Now what we'll get is we'll get a new image that is just like the base image that it had, but with one new layer on top, which is exclusively the changes the container made. Then we can use Docker save, and what that's going to give us back will be a tarball of all of those layers. This is especially useful because what you're going to get back is each layer as the differences it had on the one before. So you can look at the top layer you have in that tarball, and it's going to be everything the container changed or added as opposed to what it started running with. This is oftentimes what we're searching for when we're trying to do forensic analysis of a disk drive anyway. In this case, it just got nicely wrapped up in a bow and handed to us. Then finally, if the container is running, the other thing that we can do is we have the opportunity to actually grab process memory. Because a running Docker container is really just an ordinary Linux application, it's just got these constraints by the kernel slapped on it and its own little view of a file system. From the host viewpoint, a process inside the Docker container is also a process on the host. Well, I mean, that's handy for us. As long as you're one of those processes inside the container, you're still constrained by the kernel restrictions that are in place on there. But if you're outside in the host, yeah, if I want to kill a process inside a container and I'm the super user, I can just kill it. It's just another process. Just kill it. So in this case, the docker top command basically just lists off, here are all the processes that are running inside this container. Or put another way, here are all the processes that are running that we've slapped these kernel namespacing and C group constraints on. Once you've got the process IDs and you're running at a host level, you can just say, okay, well, these are processes. Go give me the memory. You can use a tool like gcore or whatever your preference is, and now you have memory images. So if you have a system that's already been compromised, and you suspect you're going to want some forensic artifacts out of it, it's going to be an awful lot easier to go grab them this way than pulling the plug and doing it disk-wise. We're going to go into what to happen when someone's pulled the plug and given you the disk, and sometimes in emergency situations, you don't want to spend the time, just pull the plug. But if you have the luxury of dealing with a system you control that is running with potentially compromised containers running, just grab them this way. So, cold capture. This is the situation where someone has walked up into your office and they've handed you a hard disk and they said, hey, this thing was a host that had a bunch of Docker containers on it and something went wrong. Tell us what happened. At this point, everything on the previous slide is useless. We know that most of the information that we could easily get at with Docker commands is there, but we're going to have to go at it probably the hard way. Depending upon what your tolerance is for potential alterations to an image that you're doing analysis on, you might be able to just load the thing up, stick your own little copy on write layer on it, boot it, run Docker, and grab some of the things that way. In a lot of cases, especially when you have stricter evidence requirements, you probably can't do that. You're going to have to deal with a purely read-only disk and pull out what you can from it. So in that case, if we're staring at a hard drive and we got to pull out information about the containers, where are the goodies at? varlib docker. That is, by default, the directory on any Linux system where Docker is going to store everything that we're interested in. And coincidentally, all of the relative paths that are in this slide from this point out are going to be relative to this location. So the next slide, when it has a path right at the top, that's going to be relative to varlib docker. So, first thing, there's a bunch of metadata we can go grab that's fairly easy to get at. One example is what Docker images were installed on this thing. Well, in varlib docker image, the name of whatever storage backend they're using, there is a file called repositories.json. And it basically just lists, here are all the images that were pulled down onto this host. So right off the bat, you can basically presume any container that was running probably used one of these as the base. If it was a compromised host, it might even be interesting to know what images were there, even if none of the containers that were running that you could find when the plug was pulled appeared to be using them. It may have been a very short-lived container someone used to gain lateral movement or some kind of privilege, and looking to see what images are there could be very useful. Another note, for the sake of clarity, you can see there's a bunch of SHA-256 hashes, but I've just truncated them all and made them very short and stuck ellipses after them. I'm going to keep doing that all through the presentation. So you're going to see lots of teeny little, like, 6-character SHA-256 hashes. That's just me truncating them so they fit in the slide, and this is actually readable in the back, hopefully. So there's one place. Another thing, all right, we've looked at all of the images that were pulled down onto this host. What about information for a given image? Well, once again, relative to varlib docker, there's going to be a directory, image, backend. And backend is going to be the name of their storage backend. So in this case, we're going to be looking at OVERLAY2 or DEVICEMAPPER. So if the Docker daemon that was running on this host used OVERLAY2, it's going to be image/OVERLAY2/ImageDB content SHA-256 and then the image ID. The image ID is just that long SHA-256 hash. In fact, an ID for pretty much anything in Docker is a SHA-256 hash. So that file is a really big JSON file, and it contains pretty much all the pertinent metadata you might be interested in on this image, like, for example, the image's name, the default entry point script. So if you just say docker run image name, what runs? It's going to be that entry point script, the default arguments for it. The build history. This one's interesting. Basically, it's not quite as legible as the original Docker file the image was created with, because Docker's renamed a bunch of stuff internally, but you can still see all the basic commands that were run to create this image, when the thing was made, and a lot of other metadata as well. Then what we're really interested in a lot of time is we want to know what containers we're running and what's going on with them. So once again, relative to varlib docker, there's a directory called containers, and it's going to have a whole bunch of child directories in it. Each of those is going to be a SHA-256 hash, which is the container ID. And then inside those directories is going to be a bunch of file, but the one with the really useful information is this config v2 JSON file. That's going to be more or less equivalent to what you would get if you'd run docker inspect while it was running. The other important thing to note is that containers, when Docker runs them, aren't always deleted when they stop. By default, they're left there. So this would be, what you're going to expect to find in that directory will be all the containers someone ran at some point and didn't get rid of, and all the containers that were running at the time when someone pulled the plug on this host. And there's a lot of useful information you'll find there. Obviously things like the name of the container, what was the ID of the image it was based off of, driver, which is what storage backend was used. Especially interesting when you're trying to build a timeline for what happened, the time the container started running and the time it finished running. Path and args. Just because an image has a given entry point and arguments for it that run by default does not mean that when you run a container using that image, that's what you have to use. You can specify something different. But if whatever it's going to be is going to be recorded in this container configuration JSON file. Also, all of the environment variables that were passed into this container. Mount points. This can be especially interesting. If you're looking and you're seeing a container that has mounted the root file system, just slash into the container itself, that's highly suspicious. That's probably the kind of thing you're going to find in a container that does something like, dumps the etc password file or adds something to a cron tab or some other way to basically gain persistence on the host. Obviously, there's other things like permissions, settings that could be added that would give them excessive permissions to access the host. There's a flag you can use in Docker run, which of course now that I need to say it, I immediately forget what it is. It starts with a P, blanking. Anyway, there's a flag you can pass to Docker run that basically says, yeah, all that nice little box we put around your container, throw that out, let this thing pretty much have access to the entire system if it wants it. And at that point, containerization is not really containing anything. It's more being used as a way to just deploy a software package so that it kind of has its own file system and isn't messing with other stuff. That's another thing to be looking for. The other interesting thing, back when we were looking at the live forensics capture, there was that Docker logs command. We know that could be very useful, especially if someone's running what seems like a benign container, but then issuing a bunch of commands to it over a shell session on a TTY is connected with a container. How do you grab that? Well, Docker logs is just pulling that out of whatever log storage system Docker was using. Oftentimes the default for log storage is the JSON backend, which basically just dumps another file in this directory, container ID-json.log, which is going to have all of those logs. If it's something else but still stored as a file, that log path value in the config is going to tell you where you can go find those logs, which once again can be very illuminating. I believe for the JSON backend, you also get timestamps for when individual input and output was done, which also can be very useful. You're trying to build a timeline and someone's done something like run a base Linux container and issued a bunch of commands to try to gain persistence somehow. So that's all fine and good for metadata. But what do we do about disk content? And this is where things get a lot more interesting. So you're staring at that disk someone's handed you in your office, and you want to go find out, okay, well, what did the file systems of these running containers look like? What were the changes that these containers made based off of the base image? So this is another picture taken from Docker's documentation of roughly what a Docker container file system storage is going to look like. Docker basically has all the different layers for an image. Those are read-only. And then on top of that, they stick another layer, which is read-write. And anytime the container wants to write something, it's going to get written into that thin read-write layer. Anytime it reads something, it starts at the top, looks, is that file or block there? Yes? Great, pull it out. If not, keep going down. So you basically have this stack of layers of file system or disk data that where each layer above kind of trumps the layers below, and each layer is basically including changes on the layers below. The trick is, how's all this going to get stored? So to consider that, let's have a small motivating example. Here is a really small, simple Docker container. So the Docker file, which is going to basically create the image of what our container is going to look like, does only a few things. One, it says we're going to base off of the Alpine Linux base image. So we're probably going to go pull that image down from one of their repositories and then start running these commands to build the image for our container. Then, since this example, we're basically simulating a fruit basket, we're going to add a lemons file and a pears file to the fruit directory. Then we're going to add an entry point script to run when this image is actually invoked as a container, and say, hey, look, this is the entry point script, go run it. In the entry point, this will run when the container is executed. It's basically going to add apples to the fruit basket. It's going to change our note on lemons. It's going to add a durian to the fruit basket. And then we're going to, for the sake of this example, make sure all of those changes are synchronized to disk, so nothing just stays in memory. Then we're probably going to throw the durian out of the fruit basket, because though it looked interesting, we couldn't handle the smell. And because we turned our back and the pears instantly over-ripened on us, we get rid of those too. So with this motivating example, we'll then look at what are the results we get for overlay 2 storage backends and device mapper backends, and how do we extract them. But before we get to that, what is it we're expecting to find? Well, at minimum, we're going to expect to find these 3 different layers stored somewhere, somehow. At the bottom, we're going to expect that Alpine image, Alpine Linux base image that we're building everything on. Somewhere in the middle of the stack, or at the top of our image, because remember, it's going to make multiple layers trying to build that thing, but when it's done building the image, we are going to expect to find a fruit directory that contains only lemons and pears. Then when we run the container, that thin read-write layer is going to be written down to the disk, and there we're going to expect to find apples and lemons, but no pears. And at least no remaining file for a durian, but maybe if we're lucky, we'll be able to find evidence the durian existed at some point. So this is what we're expecting to find as we go into this. So, first storage backend. Overlay 2. This is the default insofar as Docker can push it. This is what you're going to run into most of the time. In fact, I think right now, for most all Linux distributions, except for some versions of Red Hat Linux and CentOS, this is what will run by default, unless you happen to have a host file system like BTRFS or ZFS, in which case it's going to go use that. It's based off of a Linux kernel module called OVERLAYFS. The way it works is basically by each layer is stored as a directory. And what that directory contains is just other files and directories that are different from the previous layer. So if you've added a new file, it's going to add a new file to that difference directory. If you change a new file, change an existing file, it's going to add your change version of that file to the difference directory for that layer. If you remove a file or a directory, it's going to find some way to kind of add something, kind of like a tombstone, and they've got different ways of doing that, to show that that particular file or directory has been removed as compared to the previous layer. What the OVERLAYFS kernel module does then is if you give it a bunch of these different difference directories in a mount command, it can basically layer them all together, just like in that picture where at the top, what you've mounted looks like a nice flat file system. And anything you write gets written to the top layer, and only the top layer. But all the reads are going to check each layer from the top down until they find something that matches and then hand it back. So in this particular case, when Docker is using that, that means that all of these OVERLAYFS layers are going to be stored on the host file system. And that's going to wind up being interesting later on. But of course, the first thing we have to do is we have to figure out, well, how are we going to go find these layers? And of course, that's not maybe quite as easy as we like, but it's not all that horribly painful. So here's a directory tree. Basically, we start at varlib docker, and there are 2 children directories we'll be looking at from there, image and overlay 2. Image on the left, overlay 2 is on the right. We've already seen other paths that started with image, some kind of backend and then something else. Well, here the backend's overlay 2, so we're looking at image overlay 2, layer DB. That layer DB directory is basically the way Docker tries to keep track of what are all the layers in all of the images and containers I have. For containers, there's a directory called mount. And what will be inside that will be, once again, a whole bunch of SHA-256 hashes that are the container IDs for the containers that had run at some time. There'll be a bunch of files in there, but the two in particular we're interested in is one called mount ID. That's going to have a SHA-256 hash, and if we go look in that overlay 2 directory under the var Docker, we'll find a directory with the same directory name is that hash. Then there's going to be, once again, in that LayerDB mounts container ID directory, a parent file. That parent file will contain another SHA-256 hash inside of it, and that points to basically the next layer. But since you're running a container, the next layer is going to be an image layer. The image layers aren't in a mounts directory, they're in a SHA-256 directory. Why? I don't know. There would have been no collisions if they were using SHA-256 hashes for all of it, but this is the way they wanted to do it. So, similar kind of structure. Instead of a mount ID, you have a cache ID file that points over, okay, this particular overlay 2 directory, and then a parent file that will point you on to the next layer. To basically find all the layers in a given container in its image, you just start with the container, look for the parent file, move on down, until you finally hit a directory that doesn't have a parent file, and that one's the bottom. So here, basically, I've kind of cut out the other layers that we're not interested in. We just have the container layer, that image layer, and then probably the Alpine Linux base layer. Over in the overlay 2 directory, you'll have all of those SHA-256 directories, and inside of them a directory called diff. And that diff directory is the overlay 2, or the OVERLAYFS difference directory. So, given a container that looks like this, we'll make note of the overlay 2 storage hash for the container read layer is A23520. If we want to go say, all right, that's fine and dandy, I found all the difference directories, but I want to see what the container was looking at when it was running. We have to mount the thing. So, thankfully, that's not too terribly painful. You make a directory you want to mount it in, then you say mount, the type will be overlay, the source is overlay, and then because we don't care about writing, because we're not going to try to modify it, we can just say, for options, it's going to be read-only, and instead of trying to give it a merge directory and an upper directory and all that, say, here's just a whole bunch of lower directories. We're only going to be reading, so all you have to do is just stack these together. We're not going to worry about writes right now. And if we look back one, you'll see, if you look at the 3 different truncated hashes on the right side, you'll see, here they are again, in that lower dir options section, listed in the same order. The first one's the container read-write layer, and then you go from the image layers from top down, and you mount it. And if we go look inside that mounted directory, lo and behold, there are apples and lemons, which is what we expected when the container's running. Apples are there, pears are missing. So that's nice. We can actually now take a look at what the container itself was looking at before someone pulled the plug. But let's say we want to look at what the container would have had at the moment it was started, the top image layer. Well, that's actually pretty simple. In fact, the next slide is going to be almost exactly the same as this one with about one change in the mount. Here we go. Instead of 3, now there are 2. We just took that that very top A23520 diff directory that was the container read-write layer and left it off. Now it's just the top image one all the way down. And if we look inside that mounted directory, what do we find? Well, we find lemons and pears, which is good. That's what we should find. That's what the image was set at. So that means we can now mount both the container, what the container viewed, and what the container started with, and we'll look at them side by side. But a lot of times when you're doing that, what you really want to see is, well, what's the difference between these two? In that case, OVERLAYFS actually made it kind of easy for us. Because all of these diff directories are literally just differences in between layers, we can just go look at the diff without having to mount anything. So here is the diff directory for the fruit subdirectory in the container read-write layer. Apples is there, lemons is there, and pears is a character device with a major and minor number of 0. That's basically the way the kernel OVERLAYFS module denotes a file has been removed. They just make these 00 character devices. And then for directories, the way they're removed is they'll just stick an extended attribute on them. So all right, we've figured out how to mount the container read-write layer. We figured out how to mount the image layer. We can realize that a lot of times exactly what we want just by looking at this diff directory without doing anything at all. But what about that DURIAN? Remember, the container entry point script creates a file called DURIAN, and then after it sync changes to disk, promptly turns around and deletes it. Sometimes, especially if you're dealing with a container that was created by a malicious actor, they're probably going to pull some things down the disk, make use of them in memory, and then promptly delete them from disk. We're not going to find that at the lower image layer, and we're not going to find it on the file system for the container layer. Is there some way we can still get at it? Well, if this were a normal host, you could go about using normal forensic tools to try to see, okay, well, the file may have been deleted, but is the inode for it still lying around somewhere? Remember back when we introduced Overlay 2 backend, we noted that since these are just directories of differences, everything's on the host file system. In the event that something like this happens and a container's been compromised, or a host with containers that's been compromised, there's still very good merit in grabbing the entire disk image for the host. Because in this particular case, if you've done that, you can go actually find the DURIAN. In this case, I'm just using two commands from sleuthkit. One where I'm saying, okay, here's my host file system device, devsda1, and here's the full directory to where the fruit directory in the overlay to diff for the container read-write layer is. What was the inode for that? Great. Now it gives me the inode. Then I use another command. I say, okay, here's the device. Here's this inode. List the files that are in it. And by the way, let me know if there happens to be anything still dangling around that got deleted. And lo and behold, there's the DURIAN still there. So since Overlay 2 operates on a file system level on a file level, in order to grab information like this, we're still going to need a full forensic image of the underlying host disk. Now, the nice thing about all this is a couple of months ago, the Google search for what do you do with Docker storage forensics got slightly more useful. A guy named Romain Gaon over at Google created a nice little Python program that will basically automate mounting Overlay 2 and the older Overlay and AUFS storage backends. It's called Docker Explorer, and you can find it in Google's GitHub repo there. So if you ever find yourself in a position where all you really want to do is just mount the things, this might be an excellent place to start. So this brings us to the second and slightly more interesting backend, which is DeviceMapper. This is the one that you're probably not going to run into unless you're handed a host image that was either Red Hat Enterprise Linux or CentOS, up to, I think, like the very most recent version of Red Hat Enterprise Linux. The way this one works is by using the Linux kernel DeviceMapper system and the Linux volume management system, or logical volume management system. Basically what Docker does is it says, okay, we're not going to store things in the host file system. You're going to give me an actual disk for this thing. We're going to entrust that disk or disks to LVM, and I'm going to go make a volume on that disk that is going to be the base device. What they're going to do on that base device is they're going to go set up a file system. In a lot of cases, I've seen that file system is XFS. And they're going to leave it completely blank. Then, every time they need to make a new layer, they're going to snapshot that base device. And if they want to make a layer on that layer, they're going to snapshot the first layer to get the second layer and have the new changes there, all the way up till they've built all the layers for an image. When they run a container, they're going to snapshot the top device of the image and get a new device that will be used for storing all the writes from the container. So in this case, instead of dealing with files and directories, we're going to be dealing with block devices. And instead of finding the data in convenient places under varlib Docker, we're going to have to go mess around with DeviceMapper and thin pool snapshots to be able to get our hands on it. But before we can do any of that, we still have the same problem. How do we find the layers? In this case, thankfully, it's more or less exactly the way it worked with OVERLAYFS. Except we note here, varlib Docker image, instead of saying Overlay 2, now it says DeviceMapper. But everything under that on the image left side remains the same. It's still the same layer DB directory structure, still the same parent pointers to each layer beneath, still the same mount ID and cache IDs. What's different on the right is instead of having an overlay2 directory and a bunch of diff directories underneath, we have a device mapper directory with a metadata subdirectory and a bunch of files that each contain metadata we're going to need to be able to try to get our hands on the virtual block device for a given layer. Before we get our hands on it, first we're going to have to look at how we go about doing that. So the nomenclature here can be a little bit confusing. DM setup create. It makes you think, okay, well, I'm about to create a new thin pool layer. No, we're creating the device for an existing thin pool volume. DM setup is the command you generally use to interact with the device mapper backend. In this case, we're going to create a new device. Table is the option you hand to basically say, okay, here's the information to go with. And then we're going to have to give it a couple of things. A starting sector off of that base volume. The size in sectors that this virtual snapshot device extends. It's going to be a thin snapshot, so we say thin. Then for thin, we have to give it what's the base pool device we're doing all of this off of. And what's the volume ID. So all of these little layer snapshots are going to have different volume IDs. So how are we going to go about doing this? Well, to access one of these layers, first of all, note the asterisk. You actually have to have the Docker volume LVM mount activated. That's a little outside the scope of this talk, but if you run into that and you have some difficulty, just Google forensics wiki LVM, and there's a very nice explanation on how to do it. What that will get us will be a device called /dev docker thinpool. So that's the base device. That metadata file from the branch on the right we saw slides back, that's a JSON file. It's got a couple of fields in it. The two we're interested in are the device ID and the size, because that gives us the remaining information we need to hand the DM setup. So we'll hand DM setup, create, give it whatever name we want for this new device table. It's always going to start at 0. And then the size is the size from the metadata file divided by 512. And that's because device mapper always uses sectors of 512 bytes. Because Docker is recording the size in bytes and device mapper wants it in sectors, we have to divide by 512. Thin, dev, docker, thinpool. And then the most important part to figure out which layer are we getting is that device ID. Once you've done that, what you'll have is a regular, ordinary Linux block device, just like you would have for a physical hard drive, sitting at dev mapper dk my container. And if you look at it with files, say, hey, look, this is an XFS file system. So at this point, gaining access to the data is fairly mundane. Make a directory to mount it on, mount the device onto the directory you want, with one little caveat. If you try to do this twice at the same time, the second time is probably going to fail. Unless you put this no UUID option in. And the reason for that is, remember they had that base device at the bottom, and they put a file system there that's empty. And from that point, they were just snapshotting it. Well, the file system is going to have a UUID built into it. And all the snapshot file systems are going to have the same UUID built into it. So when you go try to mount the XFS file system, once, it's like, great, yeah, this UUID is not in use, we're good. Then you try to mount a different one. It's like, no, you already mounted that. And you have to say, well, actually, we're kind of breaking your expectations for how universal this universally unique identifier is. It's actually different, trust me. Just ignore that, it's okay. So if you leave that off and you run them out the second time to try to get at a different layer and you get this error that makes it sound like it's corrupt, it's probably not, just add that on. All right, so that's how we got at the container read-write layer. Sure enough, we've got apples and lemons. So what can we do from here? Well, what we have at this point are these thin pool devices. We can get one for each layer. The process is exactly the same, whether it's the container read-write layer or one of the image layers. Just go use the layer DB chain, figure out which metadata file it is, pull out the device ID and size, and off you go. But the really cool thing is, this more or less acts like what we have are these little virtual hard disks. So instead of having to monkey around with doing things differently, if you really wanted to, you could just use your imaging tool of choice and just image one of these things and go to town later. The nice thing is that because you have the lower layers, you could, say, image the container read-write layer and image the image layer directly beneath it. Now you'd have 2 disk images, and you can just compare them and see what the differences are. The other thing, and this one's for those who are reckless or bold apart, there is a tool called ThinDump. It's not terribly user-friendly. You're going to have to muck around with the kernel to get a metadata snapshot, but what it will do is basically dump all of the metadata that the device mapper kernel module is maintaining for these thin pools. The reason that's useful, or could be useful if you want to go that route, is that if you think back to that, let's see if I can actually find that diagram again real quickly. Here. If you look back at this diagram again, you have a base device and a whole bunch of snapshots on top of it. And we know anytime you have to do a read, it's going to start at the top of one of those little towers and go down until it finds something that matches. Well, all the device mapper is actually doing underneath the hood is it's got that big base device and a volume underneath it in the LVM storage pool. And it's got a whole bunch of blocks there. And so it's like, okay, I'm going to start handing out blocks to people. So for the first base device, it gets a whole bunch of blocks. Then when you do a snapshot, anytime you make a change, it's going to hand out a new block to that snapshot. And so now the data for that snapshot from that change is going to be stored somewhere else in the volume. What Device Mapper is doing inside is it's just basically maintaining a nice little list of, okay, given snapshot, which blocks in the snapshot point to which blocks in the volume. And that's it. That's all it really is. All it does is if it's a new write's done, it's just going to change that and say, okay, well, you used to point to the block that the layer below was using, but now you're pointing to this new one. So if you're able to, there we go. If you're able to dump out all that metadata with ThinDump, you can basically say, look at, okay, which blocks were pointing to what other blocks at the container read-write layer, and which ones were pointing to what other blocks at the image layer directly beneath it. And now you know exactly which places on disks something changed at. This can be more useful, and depending upon the size of what you're dealing with, more practical than trying to do a block-by-block comparison of both devices all the way to the end. You could be dealing with, gigabytes and gigabytes of data and waiting for a while, whereas there might be only like 2 or 3 blocks that changed. This would also potentially be a nice way to find the DURIAN. Remember, we created and deleted it. You could go rip open the file system with XFSDB and hunt down through all the file system metadata and find the directory thing it was in, and like, oh yeah, well that was one of those smaller directories where basically we lost all information once the file was deleted. Great. But the block that was changed on disk is still there. So using ThinDump might be one way for the more bold and comfortable messing around with directly interfacing with device mapper kernel stuff to pull out just the blocks that changed and compare them there. In summary, if you're dealing with a cold disk, you've got a bunch of metadata JSON files that will give you more or less the equivalence of Docker inspect would give you for a container or an image. You have this layer DB directory that basically gives you a chain to start from any given image or container or any given layer and figure out what are the layers beneath all of it. And then depending upon what your backend is, you're either going to have the overlay2 directory that will have all of these directories of differences, or a device mapper directory that's going to have all these virtual disk snapshots. So I realized this was kind of lots of texty terminally technical talk, so I made sure to bake in plenty of time for questions at the end. So we have time for that. And as a bonus, I also put together a cheat sheet for you all. It's just a one-page landscape letter cheat sheet that contains the high points of this that would basically get you access to the device mapper overlay backends and show you the layer DB tree and show you where some of the metadata JSON is. So, questions? Yes?
What initiates a new layer? Is it just a reboot of the restart?
What initiates a new layer? Well, you're going to get a new layer in one of 2 ways. New layers are built when you're creating an image, which is basically a series of Docker commit commands. And Actually, that's not really true. New layers are created when you run a container. So you have an image, you hand it to Docker and say, run this thing. A running image is now basically a container. And when a container runs, Docker will take it will create a new empty read-write layer on top of whatever else is there. So you get a new layer when you run a container. The way you build up an image full of layers is that, let's see if I can find that Docker file I showed you. Yeah, the example here. So that Docker file, every line in that file is going to create a new layer in the image. The first line's going to go grab the Alpine Linux image. That's my base set, and it's actually only got one layer to it. Then when I say add elements in pairs, what Docker actually does is basically it does a Docker run on the Alpine image, and it basically copies 2 files in, and then it's done. And now it says Docker commit, which takes the container read-write layer and makes it part of the image I'm building up. And it does that for each step.
So does it ever consolidate the layer?
No. Well, no with a caveat. There's an experimental option you can turn on in Docker called squash, so that when you do a build like this, it will, as the final step, take all those layers, squish them together, and hand you just one. But yeah, generally the way you're going to get layers is, by default, it's going to be 1 layer per line in that Docker file, and then anytime you run the image, that extra container layer is slapped on top. Yes?
Is there a significant performance hit from the multitude of layers?
Yes, there is. Yes, there is. It's not a huge hit, but it's enough that if you read the Docker docs, you're going to find repeated in any of the storage backend stuff basically saying, yeah, and since we're chaining layers and layers and layers and layers and layers, if you need high write performance, maybe you should go use a volume for that. The other interesting thing is which backend you use is going to give you different performance trade-offs. So the device mapper one's kind of nice because you're just using this Linux kernel thing that really does exactly what you want. The downside is that for the thin pool, you have to say how large a thin pool block is. And I think by default Docker says 1024. Now that block's in sectors of 512 bytes. So basically you're guaranteed if I change 1 byte in a file, at minimum, I've now got half a megabyte of data that just got added to my new layer. And that can add up. OVERLAYFS, the directory differences one, is a little better in some ways. Also the way the kernel module works, the page cache for the file system is useful. So if you have a whole bunch of containers all with a common layer somewhere in the middle, and they're all trying to read that same file, it actually is that same file. Whereas with Device Mapper, it's going to be technically the same file system, but different block devices, so things get confused, and it's not always necessarily going to benefit from the page cache. So if 5 containers are reading the same thing, you're going to actually go to disk 5 times. The reason that Red Hat Linux has had to use Device Mapper for a while is mostly just because they were doing a lot of really cool stuff with SE Linux to try to contain containers a little better than they currently contain. But it didn't play very well with OVERLAYFS, and I think they just managed to get that kind of worked out, and the most recent version of Red Hat Enterprise Linux 7 can do OVERLAYFS now. Other questions? Yes?
In this case, you started with the forensic examination you have to do. After you did all this, did you find any fruit?
Yes. I was actually able to, it was kind of anytime you run into a case where you're like, okay, well, before I reinvent the wheel, let's go Google. And Google says, yeah, nope. You know you got a fun problem. So it was a fun one, but I mean, it didn't wind up being an obstacle. The nice thing about things like, well, I mean, any kind of computer system. Yes. Yeah. I can't really tell you what it was because obviously it's one of our clients. Well, I mean, that's, when you're doing incident response for people, they don't like it when you tell the stories. But yeah, the gist of it basically is that it was a host that was compromised. Once they did get in, they actually proceeded to advance their hold on the host by means of running more Docker containers. And so if you kind of play back the talk through your head, you'll hear some points where I'm talking about, yeah, they might do this, or grabbing terminal output might be nice. And It's all from experience. Any other questions? I'm kind of blinded, so is anyone in the back there? Going once? Yes. When the container is removed, maybe. It depends upon what the logging backend is. So for, and all right, I have to caveat, I haven't tested this. So if you really want to know, grab me afterwards. We can throw up a VM and we'll find out. But I would presume that for the JSON file it would be, because that container, the containers directory that has that containers, like the config v2 JSON file, that's where the JSON log file usually gets dumped, and that entire directory is gone. But the JSON log output's not the only Docker logging output. They've got like half a dozen or more. Like one of them, for example, is journald, which is just going to write it straight to the system journal. Obviously, Docker doesn't really have control to be removing things from that, and if they did, I think people would probably get very, very angry with them. Other ones are routing straight off to things like FluentD or I think Graylog. So for a lot of the logging backends, actually, even if the container is removed, the logging data is probably still there somewhere. It just depends upon which backend that they use as to where you're going to find it. Unblind myself so I can, yes, way, way, way in the back. Was that a question? No. Just someone stretching.
All right, I got a question.
Yes.
So you mentioned earlier how the cold analysis is much more difficult than the hot analysis, but my first reaction when I discovered I've been hacked is get it off the network.
Right.
How do you reconcile with shut it down with what we need to figure out what happened?
That's going to come down to your own judgment and your own policies. The question was basically, you have a trade-off between the easiness of grabbing data if the system's still live versus if something's just got infected or hacked, I'm going to pull the plug right away. What's the trade-off? Like, how do you decide what to do? And my answer is basically, it's going to depend upon your own judgment and the circumstances. So in a lot of cases, probably, yeah, pull the plug. It's going to be harder, but I made you cheat sheet. The one case I would think of where it might be worth considering not pulling the plug is if you're dealing with a situation where you have a high suspicion that the adversary you're dealing with is going to be clever enough not to write anything to disk. In that case, the only thing you've got is memory. So what you might consider doing, if you think about, okay, at what point do I realize the system's been compromised? Well, probably a little while after it's already been compromised. So there's already a time window the attacker's been operating in. So the question now is, how much more time am I willing to give them, and is the added risk from giving that time worth the payoff? If, for example, you sat down and you wrote yourself a script that could, in the matter of milliseconds, go enumerate every Docker container on a host, pull down all the memory, write it to disk, make sure that's synced to the file system, and then cut power, all right, if you've got an additional time window of a couple of milliseconds, but what you gain from that is the ability to actually look at what the contents of memory was, maybe that's a worthwhile trade-off. Or maybe if it's in something that's a really, really critical system and you're willing to say, all right, I might not be able to solve the puzzle of what happened here, but at least I didn't give them the extra 100 milliseconds. Just straight pull the plug. Ultimately, it's really going to come down to like your gut, knowing your organization and knowing what your trade-offs are. But yeah, the memory case is the one case where I would consider possibly giving them that additional couple hundred milliseconds, or maybe even a couple of seconds if it's a slow system worth of time. But that would probably be only if you had a ready-made automated tool to do it and just hit the button and go. Other questions? I have not sat down and done that, mostly because my wife and I just had a delightful little boy who's now 7 months, and he's kept me quite busy. Thank you. But I mean, I will say, I mean, one of the things that my company does offer is tailored software solutions. If you have someone who wants to pay for that done, talk to me afterwards. We might be able to make it happen. Anyone else? All right.